Okay, last time we got together, we talked about relativistic kinetic energy and Einstein's famous equation. And if you look somewhere on my page, you'll find where I use my version of deriving Einstein's famous equation, and you'll see what we went through in that derivation. And so what we came up with was kinetic energy, relativistic kinetic energy, is equal to m naught rest mass times c squared times the quantity 1 divided by the square root of 1 minus v squared over c squared minus 1. That's what we came up with. And that's exactly equal to Einstein's equation. Einstein is total genius in how he came up with that. He used James Clerk Maxwell's electrodynamic equations. Very difficult. But anyway, now we're going to talk about relativistic kinetic energy. But first, before we talk about that, let's talk about Newton's cradle. Because Newton's cradle, designed by Isaac Newton, demonstrates the conservation of momentum and the conservation of energy, which is kinetic energy. Okay. And how Newton's cradle works? Well, one of the balls, there's what, 5 balls here. Either a ball on either end is raised to a certain height and released, and that ball transfers via some shock wave its kinetic energy and momentum to the remaining balls, and each ball transfers that energy to the next ball until it gets to the last ball. Then the last ball rises, converts that energy to velocity, and it rises to a certain height, stops, then returns and delivers that energy again to the remaining balls, and the end ball does the same thing, converts that energy to velocity and rises to a certain height and stops, and so on, and the sequence continues. So you can buy these Newton cradles at Amazon.com, and they're nice to have on your desk. Very entertaining. So let's see how it works. Newton's cradle. It's an amazing piece of work. Now, you don't have to take one ball and raise it to a certain height. You can take 2 or 3 balls and raise them to a certain height. Matter of fact, you can take the end 2 balls and drop them on either end and drop them at the same time and get some weird configurations. It's nice to play with. Okay? So, let's talk about what Newton's cradle does. So what Newton's cradle does is it demonstrates the conservation of energy and momentum. And so one ball is raised to a certain height and released. And when that ball strikes the remaining 4 balls here, the remaining 4 balls delivers that energy to the 5th ball, and it rises to a certain height. And so essentially what that is potential energy is converted to kinetic energy. So the PE is equal to KE, potential energy, kinetic energy. And so potential energy is m naught, the rest mass, times G times the height that it rises to. And that's equal to the kinetic energy, which is m naught divided by 2, the rest mass divided by 2, times v squared, which is the velocity. And as you can see, the masses cancel out, so the masses aren't involved in the equation. So if you solve for x, if you solve for h, you'll get h equals v squared divided by 2g. Okay. And so you can determine what height you want the balls to rise to, if the velocity is not determined. Or you can determine the velocity and calculate the height. Okay, our example using work done equals change in kinetic energy that I did on my Facebook page somewhere down there. I've done a lot of videos. But if you look for that calculation, I came up with the change in energy is equal to m naught, rest mass, times c squared, the speed of light, times the quantity 1 divided by the square root of 1 minus v squared over c squared minus 1. And that's equal to the kinetic energy. Okay? All right? The relativistic kinetic energy. Okay. So, Albert Einstein, using James Clerk Maxwell's electrodynamic equations, came up with the same thing. And I shouldn't say same thing because it was done way before I was even born. I came up with the same thing. I'm nowhere near a genius like Albert Einstein, so I'm not trying to take any credit from him. So I should say I came up with the same equation after knowing what it is, because he's done it. He's a total genius. But Mr. Einstein called his kinetic energy W. Okay? And it's the same equation as what I had come up with, and he called it kinetic energy. Okay? And that's what I'm calling the relativistic kinetic energy. Okay? So, what did I do with the work done? In my method, I said work done is equal to the change in kinetic energy, because that's what it is. Whenever you do work on something, you change its kinetic energy. Okay. So, what I said was, I proposed that someone, or you or someone else, was sitting in a rocket in deep space, absolutely still. And I say deep space because I want to make sure that you are very far away from any massive objects. And the reason why is because I want you and your rocket to be in flat space-time, where there's no curvature of space. And according to Albert Einstein, mass curves space. So I want you to be in deep space where there are no massive objects near you. So therefore, your kinetic energy at 0, k sub 0, is equal to 0. And I'm going to come along, and I've devised a method to where I can nudge your rocket a little bit every hour, every day, every second, until you reach relativistic velocities. And your kinetic energy at these relativistic velocities will be relativistic kinetic energy. And when I say relativistic velocities, I mean a velocity that's a certain percentage of the speed of light. Okay? It's very, very, very fast. So therefore, if the relativistic kinetic energy is equal to k E sub r, then the change in energy is the k E sub r minus the k E sub 0 that you had in the beginning. And I subtract those two, and k sub E is equal to 0. So the change in energy is equal to the kinetic energy sub r. So therefore, the kinetic energy sub r is equal to that equation we came up with, m naught times c squared over times 1 divided by the square root of 1 minus v squared over c squared minus 1. And if we multiply it through by Einstein's famous equation, m naught times c squared, we get m naught times c squared divided by the square root of 1 minus v squared over c squared minus m naught times c squared. And m naught divided by the square root of 1 minus v squared over c squared is relativistic mass. So essentially, this relativistic kinetic energy is equal to the relativistic mass times c squared minus your rest mass. And that's what m naught c squared is, your rest mass. Well, essentially, m naught divided by the square root of 1 minus v squared over c squared is your relativistic mass minus times c squared minus Einstein's famous equation. M naught times c squared is equal to energy, your rest energy. Okay. So let's go on and see where we were from here. So okay, we came up with this equation in one of my videos down below, somewhere on my Facebook page, and we want to prove for velocities v much less than the speed of light that this k e sub r, this kinetic energy, relativistic kinetic energy, at these much smaller velocity will come out to be equal to the regular kinetic energy, which is 1/2 the mass m naught rest mass times v squared, whatever that v is. And I'm saying v is much less than c. Okay. And I say v much less than c, even if you're flying in an airplane. Okay. Even if you're in space traveling at 26 miles per second is much less than the speed of light. Okay. So let's rewrite our equation. And here's our equation we came up with. K E sub r, where c equals the speed of light, v is a velocity much less than c, much less than c, and c, well, we call the speed of light. For those that don't know c, why we call the speed of light c? Well, we call velocity v, but why we call the speed of light c? Well, we call it c because it's equal to celeritas, a Latin word meaning swift. Okay, so that's why c is, the speed of light is called c, because it's a Latin word. It comes from the first letter of the Latin word, and it means swift. Okay, so here's our equation we derived, and in order to perform the above multiplication, we have to convert this function right here to a polynomial. Okay, and we're not going to use the binomial equation, because there's n is a negative number. So I have a much better way of converting this to a polynomial. To do this, we can use what is learned in calculus as the Taylor's theorem. Okay, and Taylor's theorem converts a function to a polynomial as such. Let's call our polynomial a plus x to the power of n. Here is our equation, our function here. 1 minus v squared over c squared raised to the power of minus 1/2. But let's take this function and to represent that, okay, and plug it into Taylor's theorem, and then see what Taylor's theorem does with this, and then we can substitute our function into that. Okay, so our f of x is equal to a plus x raised to the power of n. Let's call that equation 1. Then taking derivatives, changing y with respect to x, you learned that in calculus. We're going to call that equal to f of x to the power of 1. Okay. And then take the derivative of equation 1, we call f of x to the power of 1 is equal to n times a plus x raised to the power of n minus 1. Okay. That's going to be the first derivative. Now we're going to take the second derivative of equation 2. Okay, and the second derivative of equation 2 is f of x, second derivative 2. That's not the power 2, that just means the second derivative. That's equal to n minus 1 times n minus 1 times n, times a plus x raised to the power of n minus 1 minus 1. And that comes up with, gives us minus 2. Then we take the third derivative of equation 3. Okay, and we come up with n minus 2 times n minus 1 times a plus x raised to the power of n minus 2 minus 1, which gives us minus 3. Then we take the fourth derivative, and we come up with n times n minus 1 times n minus 2 times n minus 3 times a plus x raised to the power of n minus 3 minus 1, which gives us minus 4. Okay? So, setting x equals to 0 in our function is after derivatives, we're going to set x equal to 0. So that's going to be, everywhere you see an x is going to be 0. Then we're going to calculate that out. So setting x equal to 0 in our function, this is Taylor's theorem. Taylor's theorem says the function set at x equals 0 plus the first derivative set at x equals 0 times x plus the second derivative set at x equals 0 times x squared divided by 2 factorial. 2 factorial is 2 times 1. Plus the third derivative, where x is set equal to 0, times x cubed times divided by 3 factorial. 3 factorial is 3 times 2 times 1. And plus f of x set at 0 times the fourth derivative times x raised to the power of 4 divided by 4 factorial. 4 factorial is 4 times 3 times 2 times 1. And we go on and on and on to how many places we want to, how many derivatives we want to go. Okay? So in our previous equation, we said x equals 0, and we get a raised to the power of n. In our second derivative, we said x equals 0. We get n times a plus x, but x is 0, so a raised to the power of n minus 1. In our second derivative, we get n times n minus 1 times a plus x raised to the power of n minus 2, but since x equals 0, that's a raised to the power of n minus 2. And so on with our third derivative and fourth derivative. Okay. And also in our equation, a is equal to 1. So 1 raised to any power is just 1. Okay. So in our original equation is 1 minus v squared over c squared raised to the power of minus 1/2, where f of x equals a plus x raised to the power of n. A is 1, x is equal to minus v squared over c squared, right there, and n is equal to minus 1/2, right there. Okay. So if we solve all of these right here, and we replace these variables into all of our derivatives, we replace 1, a with 1, and we replace n equals 1 minus 1/2. Where everywhere you see a minus 1/2, we're going to replace it. And we're going to replace x equal minus v squared over c squared in our Taylor's theorem. So we're going to take all of these f of zeros and put it in our Taylor's theorem. We're going to take x and replace it in our Taylor's theorem. So let's see what we're going to do here. So this is the Taylor's theorem. X is equal to this. And so now we have, in our first equation, a is equal to 1. A plus x raised to the power of n. Well, if x is 0, that's a raised to the power of minus 1/2. In our first derivative, we replace x equals 0, and we get a raised to the power of minus 1/2 minus 1. And we just multiply these out and replacing these derivatives where x equals 0. Okay. So the function is 1. The first derivative is minus 1/2. Second derivative is minus 3/4. Third derivative is minus 1/2 times minus 3/4 times minus 5/2 is equal to minus 15/8. Fourth derivative, multiply those out, and is equal to 105 divided by 16. Okay. Now we're going to put these f of zeros in each place in Taylor's theorem, and we're going to put an x equals minus v squared over c squared wherever there's an x. Okay. Then that's what we did here. And now we have to multiply these out. Okay. You'll notice that minus v squared over c squared raised to the power of 2 squared makes that a positive. Minus v squared over c squared raised to the power of 3 makes that a negative. It's a squared times itself one more time, makes it a negative, but then we have a negative 15/8 out here, so that makes it a positive. So all of these come out to be positive, and minus 1/2 times minus v squared over c squared makes that a positive. Okay. So essentially, after we multiply these out, these numbers here become very small, because you see we have speed of light raised to the power of 8, and the speed of light is 3 times 10 to the 8th. Okay. Or 186,000 miles per second raised to the power of 8, which is a huge number. Okay. And the power of 6 is a huge number. The power of 4 is a huge number. So if we got a smaller number multiplied by a very huge number, these are essentially 0. Okay, so essentially our solution is this part right here, because these are essentially 0. So our original equation, kinetic energy relativistic, is equal to m naught c squared times 1 minus v squared over c squared raised to the power of minus 1/2 minus m naught c squared. That's our original equation. Here's Taylor's theorem, okay, which we developed from taking the derivatives of this function, okay? And then what we do is, since these are very small, this is our solution. And we plug our solution into here or here. This is the same equation now with our solution, okay? Now, so we're multiplying through by m naught c squared, and what we do is m naught c squared times 1 is m naught c squared. M naught c squared times v squared over 2c squared is m naught c squared v squared divided by 2c squared, okay, minus m naught c squared. Well, m naught c squared plus m naught c squared minus m naught c squared equals 0, okay? And that leaves us with m naught c squared times v squared divided by 2c squared. Well, the c squareds cancel. And so our kinetic energy, relativistic kinetic energy, at v many times less than c equals our regular kinetic energy at low speeds, m naught times v squared over 2. And so therefore, Einstein equation is absolutely correct for kinetic energy. Until next time, I hope you learned something.